Okay, so last time we were talking about maximum and minimum. Oops. Maximum and minimum values. And so here we have we've got an example of a function here. Who would I like to talk to? Elijah. Hello, your turn to think. So here we have a function. Which one of those statements is true? Okay, so the statement is based up of two things. It's asking where the function derivative is zero. How many places is this function got a derivative that is zero? Nope, 2. Right. So remember, derivative being 0 means it's flat. So it's flat at 2 places, here and here. Okay. Secondly, we talked about that the way that we search for local maxima or local minima. So maxima is actually the plural of maximum. Or we could call them an extrema. An extremum is something which is either a minimum or a maximum. Anyway, so we've got 2 local extrema. What type of extremum is it? Are they maximums or are they minimums? Or is there one of each? One of each, right. So here we have a little hill. So here we have a local maximum, here we have a local minimum. And so we see that C was the correct answer. The derivative was at 2 values of x. One is a local maximum. Oh no, hang on. Oh no, B, sorry. One is a local maximum while the other is a local minimum. Okay. What's the date today? Today's the 17th, isn't it? Is Peyton here? He is right there. Okay, you can be next. Okay. So here, oops, sorry. You can see that. Okay, so this is a table of the derivative. Aha, remember how I like to trick you by sometimes giving you the derivative, sometimes the function and whatever. When was the temperature a local minimum? 10. Let's have a look. Very good. You went for where the derivative is 0. And so now you've got to do the first derivative test. So beforehand, we saw the temperature was going down. Afterwards, you see the temperature is going up. Everyone agree that this is a minimum? Yep. Thank you, Peyton. Joe, are you with us? Are you paying attention? Can you unmute yourself? Yeah. What about this? How about this one? So, can you see the question?
Yeah. Yeah, I can see it. Can you hear me?
Yes, we can hear you really nicely.
Okay.
So, you've got some pieces of information and you want to conclude with certainty that there was a local maximum of temperature at some time after 10 a.m. and before 2 p.m. Which one of those pieces of information would enable you to conclude that?
C.
C, let's have a look. The temperature rising at 10 a.m. and falling at 2 p.m. Exactly right. So if something is rising beforehand and it's falling afterwards, somewhere in between, there has to be a little mountain. Thanks a lot, Joe.
Yep, no problem.
Okay. Ellie, it's up to you now. What about this one? This is a graph of the derivative. So remember, it's a graph of the derivative. It's not a graph of the function. What can you conclude from the graph of the derivative?
Would it be B?
B. Okay, the derivative is 0 at two values of x. Okay, here and here. Very good. So when you said B, what did you say?
I said B.
B. Okay, so in here, the function is rising and then it's falling. So there's a local max here, right? What about here? Here, beforehand, the thing was falling because the slope is negative, and afterwards it's falling. So it's neither. So we've got a local maximum and a neither. Which one's that? It was C.
How is the first one rising?
Sorry?
How is like the first one of your rising? Like, isn't it decreasing?
It's deep, but this is the derivative. So this is where I'm being C. So this is a graph of the derivative. The graph of the function, right? The function is increasing over this interval because the derivative is positive, and it's decreasing over everywhere else. So it's increasing up to here and it's decreasing afterwards because the derivative is positive means increasing, derivative negative means decreasing. So B is the correct answer if this was a graph of f. It's a graph of the derivative. So this tells you what the slope is. It doesn't tell you what the values of f is. Okay, so this is a good one to go back over to compare the question that was asked before. Okay, so this one is an important one to know. Eric?
So if the graph of the derivative is flat at 0, then it's neither. It's not the
So here?
Yeah.
So yeah, here it's neither because before it's decreasing, afterwards it's decreasing. If it was like this, it'd be the same because it'd be increasing flat like x cubed. It was like that. So Max, is Max here? Hey Max, can you unmute? Hi, this is your question. So we've got a derivative is continuous everywhere and changes from negative to positive at x equals a. What can you say about the function? Which one of those statements is true? We can't hear you, Max. Are you talking? Oh, he's chatted with me. Okay. Let's see what he says. Chat. So yeah, your mic's not working, Max. So you'll have to chat it with me. Just tell me. I assume you can hear me because A is a critical point. That is correct. And what else? So there's actually two statements that are correct there. Which is the other one? So if it goes from negative to positive, if f prime goes from negative to positive, what is f doing? If f prime is negative, yes, it's a local minimum, exactly. Can you see that? Oh yeah, you can see that. Right, it's negative and then positive. So not only is it a critical point, but it's a local minimum. Thank you, Max. Let's have a look at, oops, let's have a look at this one. So instead of asking people, let's just ask generally. We've got a function here. How many critical points have we got? 3, where's the, isn't it 2? Yeah. It's critical points here and here because that's where the derivative is 0.
Would it not be 2 and 1s because
Well,
like it's supposed to say it's starting.
so it looks like as it goes to infinity, it's going to go flat. So maybe out at infinity, but infinity doesn't count as a critical point. Okay. Is if this was a graph of the derivative, there'd be 1 critical point. How about this one? How many critical points do we have? So we've got all the normal ones. We've got here, 1. We've got here, 2. Here looks like there's 1 flat here, 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 and here. This is not a critical point because the function is not defined here. So if one of these things was a black dot there, then that would be a critical point. And these points, well, they're endpoints. So I would just classify them as endpoints.
So that's one critical one.
Let's say no. Let's say no. Let's keep them distinct. So how many local minima does WF have? This is now a local minimum, right? Even though it's not a critical point, it's an endpoint. So endpoint can be a local minimum. This is not a local minimum because there's no point there. This one is, and this one is. Local maxima. How many are people counting local maxima? Is anyone seeing 4? 1, 2, 3, 4. Yeah. Okay. Let's get rid of that. Okay. I'm going to stop the sharing on that. Okay. So today, yesterday we looked at when the first derivative is 0, and that basically gives us critical points, and then we can test them to see whether they're maximum or minimum or neither. Right? So the first derivative test will always definitely tell you is a max or a min or neither, right? Because you just look at whether it's plus, minus, minus, plus, 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 or minus, minus before and after. That definitely tells you. Then we had the second derivative test, and that will sometimes tell you when it's a max and sometimes tells you where it's min, depending upon whether the second derivative is positive or negative. But if the second derivative is 0, then it's still possible for it to be a max or neither. Okay. So let's have a look at the second derivative, and that's what the test for inflection points. Where am I up to? Yes. Okay. Now, what is the definition of an inflection point? See if I can write it here. An inflection point is where the function changes concavity. Okay, so it's it's the second derivative equivalent of an extremum. Okay, so remember when we had a first derivative, we look for critical points. Critical points are just points that are possible extremum, right? Because it's possible to have like an x cubed, so it's possible to be flat even though it's not an extreme value. Okay. If it is the top of a hill or the bottom of a valley, then it's an extremum. Okay. For the second derivative, we're only interested in where the concavity actually changes. So the way to do that is if we look at the second derivative, and we have a point A here, this is our inflection point. It's either plus before and minus after, or minus before and plus after. We don't make any distinction between the two types of inflection points like we do with max and mins. Okay? And so what happens at A? What does the second derivative at A have to be? 0. Typically 0, although you might have a perverse case where it does not exist or is infinity. Okay. Let me give you an example of that. So a typical inflection point looks like that. It's concave down, then concave up. Okay, so somewhere around here, it changes concavity. Another way you can do it, you can have something like this. Something kind of weird like that, where you've got some kind of corner kind of thing or some sort of cuspy kind of thing. So it's something that's kind of non-smooth, and here the second derivative would be wouldn't exist. Okay. Sorry?
What about one where it would be infinity?
I mean, it could be infinity. I'm kind of thinking it's going to be kind of like a cusp. So maybe I want it to. Trouble is, like with a cusp like this, both sides are. That's not a inflection point, right? But I'm pretty sure. Oh, yes, I know. kind of like that. So something like x to the 1/3 or something like that could be a, would have infinite second derivative. Okay, so let's do some examples. So this is going to be like a typical long problem would be, I give you a function and I ask you, tell me everything about it. So say, for example, you want to graph this without using a graphing calculator. So the things I would be interested in, the most important things I'd be interested in would be when is it increasing, where is it decreasing, when is it concave up, where is it concave down. So they're the basic facts I like to know about a function. So that means you need to know the transition points. So that means you need to know what are the critical points and what are the inflection points. So like a basic standard long problem would be, I give you a function and then you start taking derivatives. And you start setting it equal to 0. So this would be 3 times x squared minus 1. This is 6x equals 0. So the critical points are what? When is this equal to 0?
3.
No, not 3. Plus or minus 1. The 3 there is kind of a red herring. It doesn't really do anything. And then inflection points would be when x equals 0, but maybe. All we know so these are definitely critical points, but we don't know what they are. They could be a maximum, they could be a minimum, they could be either. X equals 0 could be an inflection point, but only if concavity changes. But it's obvious concavity changes, because what is 6x when x is negative? What is it when x is positive? It goes from negative to positive, so it is an inflection point. And then for the critical points, you don't know what they are, but then you just do minus 1. Oh, actually, we can do the second derivative test. What's the second derivative when x is 1? It's positive, right? So when x is 1, it's a minimum. When x is minus 1, the second derivative is negative, so it's a maximum. This is the inflection point. And really, those are the key facts that I would be looking for. So this describes this function really, all its behavior. Oh.
How would I grab that?
Then it's pretty easy. So all you've got to do is worry about 0, 1, and minus 1. So 0, so here's minus 1, 0, 1. At minus 1, it's minus 1 plus 3 is 12. This is 12. At 0, it's 10. And at 1, it's 8. And so what have we got? We've got a max and a min. Okay, so it must look like this. Goes through here, changes thing, and so it must look like that. There's the max, there's the min, that's where it changes from cavity. So that's all the relevant information you need to show me. And really, we're not really interested over here or here because it just goes off to minus infinity and infinity. You guys at home, is it mirror imaged for you?
No. It looks
Oh,
fine.
good, because it's a mirror image for us here. So, okay. Thank you. Let's do another one. X to the 4th. Okay. This is a nice easy one because we can differentiate this till the cows come home, right? Okay, it's just easy power law. So what's the critical point? X equals 0, right? Inflection point. X equals 0, question mark. Oh, this is interesting. It's both a critical point and an inflection point. Okay. What's happening here? Okay. So let's have a look at the derivative. The first derivative. What happens when x is negative? What happens to the first derivative? Negative. What happens when x is positive? What do we got here then? It's a minimum. Let's have a look at the second derivative. What happens when x is negative? What happens when x is positive? It's not an inflection point. It's just a minimum. And in fact, we know what x to the 4th looks like. It kind of looks like a parabola, except it's kind of more weighted down near it's flatter at the origin. Okay. Okay. So this one, that one was I would call that an easy one. Let's do something a little harder. How about f of x equals x times e to the minus x? Okay, so this one we have to use our skill at differentiating. Just a product rule. It's x times minus e to the minus x, that's the derivative of that, plus 1 times e to the minus x equals e to the minus x e to the minus x. Okay, define critical points. Let's factor it out. And after we factor it out, hopefully you can see straight away what the critical point is. X equals 1, right? Let's do the second derivative then. Derivative of e to the minus x is minus e to the minus x minus, now the derivative of x times e to the minus x, well, we just did that here. And so we multiply it out, so we get minus 2e to the minus x. Minus times minus is a plus. And straight away we can see the possible inflection point is 2. X equals 2 inflection. So we found our candidates. Next, we test them out. Here's one. What happens if x is negative? X is less than 1. It's positive. And x greater than 1? Yep. When it's got linear factors like this, it's really easy because it's a linear factor, it has to change sign when it goes through it. Okay, so this is, we've got a max. Okay, we do the same thing with the 2. When x is less than 2, something like 1, what is it? Negative. And if x is greater than 2, positive. So it is an inflection point. So we've got a max at 1, a min at an inflection point at 2. And that's enough information for you to actually graph it as well. Along with the fact, you've got to figure out what happens as x goes to infinity, I guess. But that's pretty good because that's, x to the 4th was, I would say, is an easy function. This is kind of like a hard function, but again, we can just figure things out. Let's do one more. Let's do another cubic function. Let's do x cubed on 6 minus x squared on 4 plus x, minus x plus 2. What is the effect of this plus 2? It doesn't affect a critical point or inflection point at all. All it does is it moves the function up and down. So when we take its derivative, the plus 2 goes away. We get, what is it, x squared on 2 minus x on 2 minus 1. Then we can go ahead and we can find critical points by using the quadratic formula. Okay, we'd have to use the quadratic formula. We do x equals a half plus or minus square root of minus a half squared is a quarter minus 4 times a half times minus 1. Divided by 2a, which is 1. Half plus or minus, this is 2 1/4, square root of 9 over 4. What's the square root of 9 over 4? 3 over 2. 1/2 plus or minus 3 over 2. So x equals 2. Or minus 1 are the critical points. Okay. Okay, so this is one's a little bit harder. You have to use a quadratic equation. So second derivative is going to be easy because that's just going to give us something linear. We're going to get, down comes a 2, we're going to get x minus a half. So we're going to get x equals a half as an inflection point. And we're going to see straight away that's an inflection point, right? Because when x is less than a half, it's going to be negative, and when x is greater than a half, it's going to be positive. So when it's a linear factor like that, straight away you see that it's an inflection point. And for this one, let's do the second derivative test. When x is 2, the second derivative is positive, so this is a min. When x is minus 1, this is minus 1.5, so this is a max. And if you do enough cubics, you'll notice that if you have a cubic like this, which is positive, like this, all cubics kind of look like this, right? So you're always going to get a max before the min and the inflection point between the max and a min. They always, after a while, you do enough of that, so that's a way that you can kind of double check that things are sort of going okay. Anyone got any questions about this? Let's see if I can do a little bit of a graphical problem. Okay, here's an example of a graphical problem. So here is a graph of f double x, the second derivative. Okay, so where is the inflection point or points for x, for the function f? Hmm? So let's have a look. So possible inflection points are going to be when the second derivative is 0, right? It's 0 at 2 points. It's 0 here and it's 0 here. Now, is this an inflection point? Will this give us an inflection point for f? No, right? Because beforehand it's negative, afterhand it's negative. So the function straightens, but it doesn't change concavity before and after. What about this point here? Right? Beforehand, the second derivative is positive. Afterwards, the second derivative is negative. So it goes from positive, which means concave up, to concave down. So this is an inflection point. Okay, so all this way, the second derivative is positive, so it is concave up. And that's the function f. F is concave up. Here, on this side, the second derivative is negative, so that means it's f is concave down. There's only one place where it changes concavity, and this is this place here. Okay, so you kind of notice that there's this subtle little question I can give you where I I give you a function, or I give you a derivative, or I give you the second derivative, and I ask about some other function. So you've got to translate what you know, right? You've got to understand what is the meaning of inflection point, change in concavity. Okay, that can be kind of sneaky. Here's another non-formula problem. Okay, we're going to fill our vase full of water so we can give our mother a bouquet, right? So our vase is kind of shaped like this. I'm terrible. Okay, does that look like a vase to you? Okay, we're going to fill it full of water. Okay, and let's say we fill the water in at a constant rate. And over here, we're going to have a function which is the height of water in bars. Okay, so obviously where the vase is wide, water goes in a constant rate, the water level is going to rise slower than it is when the vase is narrow, because then it's going to be filling the most. Okay, so what kind of function is f going to be? So firstly, so when I say that, I'm always asking two questions. I'm asking about the first derivative and I'm asking about the second derivative. So what can you tell me about the first derivative of f? I'm filling it up constantly up.
Positive.
It's positive, right? Because the water level is always going to be increasing. So that means the first derivative is always going to be positive. Okay. What about the second derivative? Well, so that's a little bit of more of a subtle question. Can anyone tell me what the second derivative is going to look like?
It's going to be negative in the first bracket.
What's going to happen? So the vase is narrowing. So what's happening to the rate at which the water level rises? It's increasing. Okay, so that means the second derivative is positive. So what does that mean? That means it's concave down. So we're going to expect concave down. But then what happens up here? What's happening to the first derivative? What's happening to the rate at which the water level is rising?
The rate decreases.
It decreases, right? Because it's getting broader and broader. So that means the second derivative is negative. So that means it's concave up, concave down. Sorry. So the rate is going down. Yes, so it's concave up. And where do we expect the inflection point to be? So which point of the vase corresponds to the inflection point in the graph over here? Right, the narrowest point right here, right? Because as it goes from here to here, the rate is increasing. So we're going to expect, hang on, did I do this? Did I mix up between concave up and concave down? It's concave up, right? Because it's going to look like that. Yes, it's concave up. Sorry. And then after it reaches that point, it starts to flatten out. So it's going to sort of go like this. It's concave down. Here's our inflection point. And it corresponds to that thing there. Okay. Okay, so that's the idea of an inflection point, and that's the kind of things that I expect you to know. I expect you to be able to figure out where the inflection point is based on the second derivative. Okay, so the only thing you can do is look. We're looking for a change in concavity, so you're looking for places where before it, it's got one sign, and on the other side of it, it's got a different sign. Okay. Okay, that's it for today, and we'll meet tomorrow. See you, Phoebe, Joe, and Max.